factors affecting acid strength. The strong bonds strong bonds does not break easily. Weaker bonds can be broken more easily. Now, what does basically this mean? For example, if you have a strong acid, HCl, it means that the bond between H and Cl is weak. That's why it can be broken easily. H can get ionized easily, and that's why it's a strong acid. So how do we define strong acids? The ones that where the hydrogen can leave easily, proton can be donated, and that is possible only if the bond is weak. So that means if the stronger acid means weaker bonds. Another way of saying is, if you have a strong acid, let's say HCl again, it produces weak conjugate base, which is Cl negative, and this weak conjugate base is very stable. So if something is producing a weak conjugate base or weak conjugate acid, then that is a strong molecule, or whether it's an acid or a base. Let's look at first in a period. Here is carbon, nitrogen, oxygen, fluorine, and the acid strength increases from left to right. For example, let's say I'm writing like this, H2O, HF. So in this, HF is most acidic. And why? What's the reason for that? Because when you go from left to right in a period, I am discussing this thing here. When you go from left to right in a period, the electronegativity increases in this direction. Electronegativity increases. And what that does, it makes the bond between hydrogen and another atom, it makes it more polar. And more polar bond can be broken easily. Or we can say the polar bond makes hydrogen easier to ionize. So when you have 2 or 3 molecules that are given, and the and those atoms basically in the molecules, they are in the period, then you compare the electronegativity. On the other hand, let's say if we talk about groups. In the group, we do not compare the electronegativity, we compare the size. For example, let's say H, again going back, HF, HCl, HBr, HI. So if you go down in a group, the size of these atoms increases. If the size increases, then the acidic character also increases. Acidic strength increases down the group. Let's look at this. Why is that? HF breaks down to produce H plus, F minus, F negative. Fluorine is smaller in size. So let's say this is the size of fluorine, this is the size of chlorine, bromine, and here is the iodine. Hydrogen is size remains same. So this size mismatch here makes the bond weaker. And if the bond becomes weaker, means hydrogen can ionize easily. So In a period, compare the electronegativity. In a group, compare the size. Oxyacids are the molecules that consist of hydrogen, oxygen, and one other non-metal. So let's look at, for example, CH3. This is a carboxylic acid, and in this one, let's say I'm replacing one hydrogen with fluorine, carboxylic acid, and here one of the hydrogen is replaced with chlorine. So these are my three examples here. The first one, I did not add anything other than it's just hydrogen and oxygens, but they are all still, so this is a carboxylic acid, the first one, and this is the hydrogen, the one that is attached to oxygen, can be ionized. And in all these three molecules, this is the hydrogen that gets ionized, means this is the one that gets donated. Now, if you look here, then what we have done is I have replaced one of the hydrogens with fluorine here, and in this case, I have replaced with chlorine. Out of these three, this one will be most acidic, and this will be least acidic. And why is that? I have replaced this hydrogen with fluorine here and chlorine here, and then you're going to compare the electronegativity of these nonmetals, and it says the acidity increases if the element, the one where is more acidic. And why is that? Fluorine is more acidic than chlorine, so what fluorine does, it attracts this pair of electrons towards itself, and due to this, and this is known as inductive effect, when electrons are moved towards fluorine, this carbon ends up getting the positive charge, then this moves here, and then this hydrogen can get ionized easily. If we are putting a more electronegative element, that means this inductive effect, that the pulling effect will be more. So fluorine is more electronegative than chlorine, that's why, oh, this is wrong, I am so sorry. Since fluorine is most electronegative, then this will be most acidic and this will be least acidic. So first, second, and third. Now, what if let's compare these acids, HIO, HIO2, HIO3, HIO4. In these several acids, these are also known as oxyacids, and the difference is they have the different number of oxygen atoms, and it says the oxyacids with more oxygen atoms is more acidic. So I can clearly see here that this has the most number of oxygen atoms, so this will be most acidic and this will be least acidic. The next is the Lewis acid base definition. For Lewis acid base, you need to know the definition, and you also need to show the electron dot diagrams. So Lewis acids are electron pair acceptors. So acids are electron pair acceptors, and Lewis bases are electron pair donors. Now, looking at so this molecule, boron trifluoride, I cannot explain the acidic or the basic character of this based on the Bronsted-Lowry acid-base definition, because Bronsted-Lowry is Acid is a proton donor, but I cannot see any proton here. I cannot see any hydrogen that can be ionized. But I can explain that based on the Lewis acid base. So for example, if you look at this reaction here, this the reaction of BF3 with ammonia is a Lewis acid base reaction that results in the formation of an adduct like this. What happens if you look at boron? Boron does not have the octet here. It has only 6 electrons. 2, 4, 6. And so it can act as an electron pair acceptor to get the octet. So what happens? This ammonia here has this non-lone pair, non-bonding electron pair, and this can act as an electron donor like this. So here, that means now we have here, and this is known as Lewis acid base adduct. So if you see a covalent bond here in the Lewis adduct, a covalent bond is formed in which this shared pair of electrons are, both of them are from the same atom, which is nitrogen. This type of bond is also known as coordinate covalent bond. Why? Because both the electrons are coming from the same atom. So very important to know this, that all Bronsted-Lowry acid bases are Lewis acids and bases, but all Lewis acid bases cannot be defined by the Bronsted-Lowry acid base definition.